This evening, I'm going to be telling you the story of what is left to discover. Well, just to warm the engines up a bit, no. Wait a minute, let me talk about the introduction first. First of all, I thought I'd write this book. What is there still to discover? Because you know that if you talk about this and refer it from here to eternity, it's too easy. But it's more difficult, if the challenge is more interesting, if we say, well, what is left to discover on the very short-term scale, something that people can maybe monitor. Since I'm an astronomist, then why don't we take Halley's Comet? Halley's, as you all know, it lasts 76 years. It passed in 86. It'll come back in 2062. Some of you will be seeing it, but it's roughly 50 years, so what is left? And I have basically said what is left to discover for the next 50 years. I started doing this for Mondadori, and it's in 7 or 8 chapters. And then personally, I like to try and also do it on television. And those are the National Geographic Channel, which is a Sky channel, said, come on, let's do it. So I sort of went with doffing my cap to Mondadori and said, thinking that then these people who belong to Berlusconi would say, no, we would only do it with Mediaset. But no, they agreed. They agreed to do something together. So in the end, we had this program, which in the end was very successful. So as an introduction, you have now, if I can find it here, you can see the first of the programs. If it all works as it should. What will we have discovered in 2062 when Halley's come back? Every year, at the beginning of December, in early December, we go to a cupboard or up in the attic to pull out the Christmas decorations. And we use this star, this cardboard star, to, in fact, assess and see what has happened. Likewise, if we have to see what has been what developments there have been in technology, we can use a real comet in the sky. We nowadays call it Halley's. For the past 2,000 years, but probably more than that, every 76 years it comes close to the Earth. But what are comets? Comets are smaller bodies of the solar systems. They're made up of ice, rocks, and volatile materials, the same ones which were used to make up planets. Every now and again, one of them, because of a particular chaotic gravitational conjuncture, goes towards the sun, passing closer to the Earth. Going towards the sun, it then meets the solar radiation, which goes against the ice, and that evaporates it. So on the other side of the sun, the comet develops along. Well, you can either call it like the tail of a comet, or it's like the hair of a comet, and it's very beautiful, and human beings have always loved them. It's like a mane. We know that Giotto di Bondone, who was a painter, saw a comet which is Halley's, and he saw it so clearly that he was able to draw it above the Nativity in the Scrovegni Chapel. Then, in the 18th century, Edmund Halley observed it more clearly, and he predicted that it would return every 76 years. So with 1910, for the first time, it was possible to take a photograph of Halley's comet. Now, when the comet came back in 1986, an entire fleet of probes and spacecraft moved towards Halley's comet, and the one which was most successful was the European one, which had been called Giotto. and it got to less than 500 kilometers from the nucleus, sending us some images which were incredible. The nucleus was as black can be. It was the blackest one we'd ever seen, an absolute black. Now the question is, what is left to discover from now to when Halley's comet will come back in 2062, well knowing that each and every discovery is the beginning of a new quest.
Questa era la prima puntata che, come dire, ci mette. Allora io ho cominciato a
So
scrivere il
this was
libro.
the first of the programs which conceptualizes it. I started writing the book, and one morning I was there writing, and on my desk the small spacecraft, the von Braun, appeared, and from the von Braun, little spacecraft, a little extraterrestrial being emerged, Mr. QFW. Some of you may have recognized him. He's the hero of Calvino's Cosmic Comic. And Calvino doesn't say much about him. He says that he's as old as the universe, so he looks as if he's quite old. And he is wonderfully symmetrical. In fact, he's a palindrome. And he speaks a language which is a galactic telepathic language, which I understood perfectly, of course. And here he's with von Braun's spacecraft. Clearly, he knows everything. He comes from who knows what funny species, and I asked him, what is there left to discover? If you can tell me, then maybe I can get the Nobel Prize for it or something else. Because he said you can't, because there's a sole peg. The peg is the postulate of galactic evolution, the PGE in English, but in Italian it was a PEG. And we certainly can't tell you humans what is going to happen. So he didn't want to tell me, but then on the sly he did help me. And in the end, basically, he wrote the book, luckily for me, and we'll see what it says. And he said to me, the best thing to do is to start and ask questions, or at least to imagine which questions we would like to have answered. So the best question which I can imagine is there anyone there outside apart from the television and problems? Wait a minute, I have to move my computer onto the stage so I can see you better and I can ask the question. Let's imagine for one moment that you're on a beautiful beach or on a mountain at night. On a mountain, you're looking up at the stars. Certainly, you can't be indifferent to looking at the stars, as Mario was saying. They're quite impressive. It's also very difficult not to ask oneself, what am I more afraid of? That we're alone in the universe, or that there's someone else in the universe? Because tertium non dato, that is to say, there is no other possibility. Either there is someone else or there isn't someone else. So think about it. So I'm asking you, who believes that there is someone else out there? Please put your hands up. Don't be afraid. Yes. Keep the hands up. Keep your hands up, because this is like a poll, like an election poll. Hands down. Who believes that we're the only ones in the universe? Well, sizable minority, but unquestionably a minority. There are no questions on that. So most of us think, without defining who, what, and where. I didn't say whether they're good, bad, whether it's a beautiful fairy godmother or a horrible alien with a killer ray. But I haven't specified that. But everybody, or most of us, believe that there is someone outside. So what do? As astronomers, we go out and look for them. So we're finding them. That is the first thing, which is very important and which I wanted to speak to you about, because we've already found about 850 planets outside the solar system. I would like to recall the fact that this is easily said because everybody said so. Giordano Bruno had said this. Unfortunately, he died in quite a painful way because of this. Giacomo Leopardi also said it. He was a poet, but in fact he was an astronomer. You don't know it but that's what he was. And now, in fact, we are observing them. And I would like to tell you that it was only 16, 17 years ago that we saw the first planet outside the solar system. Now we've seen already about 1,000. And next year, with some new space missions, we will go at 10,000. Who knows? There is an exponential increase in the distance, and there are different planets. But amongst them, one thing we're doing, we're looking for a new Earth. We found all sorts of types. So look at this one, for example. This is a planet which is distant from its sun. Its sun is very weak. So this planet is frozen. It takes 800 years to rotate around its sun. So it's very far. It's freezing cold, not much life there. While this one takes 20 hours to go around because it's very close to the star. And so the surface temperature, 2,500 to 300 degrees centigrade. And there again, no life. What we're looking for is something a bit like this one. That is to say, a planet which is the right distance from the right star. In this case, it's a 6-gold middle-aged sun, a bit like the sun. We don't want, you see, I think it should be single. We don't want twins. We want water to remain liquid because life on Earth exists because for the past 4 billion years there's been liquid water. And these are very difficult planets to find. They're relatively small planets as compared to the big ones like Jupiter or Saturn. But we're now starting to find them. And here you see this is an image which is a rather dry image, but it's fascinating because it's very, very recent. And here there are 9 planets which are rotating around these stars that have very dry names, which are linked either to the constellation or to a catalogue. Names don't matter. But what is important are these figures. That is to say, this is the Earth Similarity Index, the ESI. And you see, it's equal to 1, Earth, by definition, and 0 for an object which is completely different or incredibly different. In fact, planets with an ESI which exceeds 0.7 can or are compatible with life as we know it. Some elementary form of life, a disgusting little worm, a bacterium, or something like that. The ones that have an index which exceeds 0.8 could also have forms of life which are far more advanced. So beware, because these are very close to us. That is to say, they are within 20 light years. And we found these within 2 or 3 years. Up to 2 or 3 years ago, we had 0 planets that were close to us and very much like the Earth. Now we found them. Now, what does this mean? It means that maybe in 10 years we'll have 100, 1,000, who knows? And sooner or later we'll find the right one. We will find a planet which really is identical to the Earth, possibly somewhere where we could live. So think about this, think about what our attitude would be, the attitude of the Homo sapiens species, because Homo sapiens is called the invasive cosmopolitan by ethologists, a bit like cockroaches and mice and rats, because we invade places. But if once we discover that with the spacecraft we could move on to another planet, possibly as soon as we find another continent, we went to it, maybe we'll do the same with another planet. This still has to be discovered, but unquestionably, within 50 years, we will have discovered another Earth, that is to say, a place that can be lived in, which is close enough to us. If within the spectrum of the atmosphere we see chlorophyll, for example, that we see that there is evidence of forms of life, so much the better. And it is what we want. What? I haven't got an image in it. Here it is. In the meantime, I said we've got another 20 billion planets. This is in a very close-up view. Galaxy is very big, 100 billion stars. So there are about another 20 billion planets like large numbers, aren't they? Got to think about it. I was saying, so you're going to ask me, but E.T., because the life we have here is something which is really not really good for movies. Worms, unicellular beings. What we want is we want E.T. We want someone we can talk to. We've been trying for the past 50 years using radio telescopes of various types to see if anyone is broadcasting. That is to say, whether we receive pi or any other symbol. We haven't found them so far. I need the glass, even if it's empty. For example, it's similar to deciding if I go to the sea and I take a glass of water and I look at it, there are no fish, and I might then conclude that in the sea there are no fish. It's a rather hasty conclusion because there might be fish, but they simply swam away and we haven't found them. So basically, the universe is very big. Life very probably exists somewhere else, possibly near us. Sooner or later we'll find it. And here again, the probability of E.T. wanting to call home is something that might happen in the next 50 years. But we still have to manage the whole universe, and in particular, we have to understand matter in the universe, because less than 20 years ago, 15 years ago, we made another discovery which was devastating, which has left Einstein wide-eyed. We discovered that in the universe, we are small shareholders. That is to say, astrophysicists like me talk about this, develop telescopes, satellites, and so on. But in the end, they are dealing with 4% of the universe. We then have the remaining 96% of the universe to discover. So the younger astronomers that are here this evening are going to have to work on that 96%. What we can say very briefly, but it's a bit like whistling in the dark because you want to build up some courage, is that we call it dark matter. We don't really know what it is, but we can imagine that it has a weight. And the other part we know even less about, and so we call it dark energy. It is something which is being pushed out from the center of the universe, or something outside of the universe which attracts it. So dark energy, I have a friend of mine who's Milanese, and they're intellectuals, and she said to me, I was trying to explain to her that 2 years ago, Nobel Prize for Physics was awarded to those who've discovered the dark matter. And I said, but nobody really knows what it is. And she said, they gave the Nobel Prize to someone who doesn't know what they found. Well, it's fascinating. Yes, they awarded the Nobel Prize because they discovered something very important, but we don't know what it is. But it's very important that it does exist. So I think that we've got a bit of leeway here for new discoveries. The next generation of astronomers have 96% of the universe to work on, so pull your socks up and get to work. But even talking about energy, talking about normal energy, there's still a lot to be discovered. And in particular, I would like to spend a word on the matter of energy on our planet. Here, if we look at the field of energy, we are really lagging behind. The first big discovery in the field of energy was by the Neanderthals, or even before then. They discovered that mammoth steaks were nicer if cooked rather than raw. And then the only other significant discovery in the field of energy is the 8th of December 1942, which is what Fermi discovered when he managed to draw energy where where nature has placed it. That is to say, in the nucleus of the atom. Nuclear energy, I know that's a bad word nowadays, but nuclear energy is where nature has put what is important of energy. That is to say, the concentration, that's just what keeps us together. Without nuclear energy, we wouldn't exist, but you can't say this, so let us leave it aside for the time being. Can't mention nuclear energy. I'm a bit sick of using as energy to be using fossil fuel, which, other than being fossil fuel, means that you steal oxygen from the atmosphere, link it to carbon, and then send it away as a CO2. This is basically what keeps these lights on. You steal oxygen from the atmosphere and you send it out as CO2. And you never calculate this because oxygen is free and belongs to everyone. Well, that's another matter, but let's leave it aside for a moment. So what I would like to say is, if I look here, if I drilled a hole, just like an oil drill, like 7-8 kilometers, which is something that oil drills do, I get to a level where there's a layer of rocks that has a temperature which is around 250, 300 degrees centigrade. This is something which is always true, and it's due to the fact that the inside of the Earth is very, very warm. It's more or less made of lava. Now, every now and again, the lava spreads out, the geysers, volcanoes. But other than that, all the Earth is made like this. But if this is so, what is it? What is this? It's simple. I'll make that hole, a bit like drilling an oil drill. And then here you see there's another thing that oil drillers know how to do because they do it for gas and fracking. And I make another hole here, cold water pumping down, which going through the rocks at 250, 300 degrees becomes steam, but it comes up as steam and hot water. At that point, there's a turbine up there, and that's done. This is not a joke. You can do it, and you can have 1 gigabyte, like the nuclear ones. You can have an enormous, or you can produce an enormous part of energy, which is what we need for an advanced countries like Italy, where we consume 50 gigabytes, not crumbs, and it's electric energy, which is clean, free, and endless. There's no end to it. So in the end, this is something that we will have in the next 50 years, while we're still quarreling about nuclear or non-nuclear, because the problem of the nuclear energy is what you do with the spent material. We're going to send them back to Casale, but in any case, here you can have water which can be recycled, or we can imagine things, but it's certainly not polluting. And you don't burn oxygen. Here, the heat and energy is obtained or developed using the inner heat of the Earth, and the thermal ability of the Earth is enormous. For the human race will be enough for several million years. It's a calculation, in any case, useless calculation, because it will last more than the human race itself. So here, at this point, as you've seen, Mr. QFW has already given some interesting indications, but then the important question came, will we have discovered what life is? Because if I call one of you here, even Piero Bianucci, and I say, tell me what life is, and you probably say, you'd be a bit embarrassed and say, couldn't you ask me another question, please? Once I asked a student, tell me what you want, and he said, please, Professor, ask me another question, because that's too difficult. I didn't give him a good mark, but in any case, why don't we know what life is? Why are we unable to give an absolute and clear definition of what life is? Because we only know one, and which is the one which we're made up of, and anything else on Earth. This famous Nobel Prize for Chemistry, de Duve gave a name which is like a Brazilian cocktail, schnapps. You see here, because we have got carbon, hydrogen, oxygen, nitrogen, phosphorus, and sulfur, plus traces of other elements. but these are the most important ones. So we're schnapps. So if I have life 2.0, which, by the way, might be outside Earth, but also on Earth, and we maybe haven't found it, I could imagine that we could replace one of these atoms which comes from the table of elements, which is a very important thing that you should be aware of and know. To know how we're organized, we could replace it. For example, I could replace carbon with silica, which is the one close to it. In fact, there are a lot of science fiction stories which have thought that, but it doesn't really work because carbon is able to produce large molecules unlike other elements. Another possibility is phosphorus. Just below phosphorus, we have arsenic, which again chemically is very close to it. So we could imagine that we're going to replace it. And this sort of Madame Bovary idea came to a friend of mine, a NASA astrobiologist, who in California had found a lake, a monolake, which had a very high density of arsenic in the waters, a place where you shouldn't really go and swim. And she went to scratch it there, to scratch the mud from that, and she thought that she wouldn't find life. But incredibly, she did find bacteria at the bottom of this small lake, mountain lake, and she was convinced that these bacteria, to survive in this water which was saturated by arsenic, managed and metabolized the arsenic instead of phosphorus, and in that case they would have been life 2.0 on Earth. She published this on Science, which is a very high impact factor journal, very prestigious one, and also showed the type of DNA, or what she thought was the DNA, these green dots, in her opinion, and she convinced everyone, were arsenic instead of phosphorus. So, unfortunately, she was wrong, and soon after, they photographed these bacteria. They're very small. You see, this is 1 micron. They're very small, minute ones. But unfortunately, they live in this horrible environment, this horrible lake, and they've got arsenic, but they managed to englobe it in these whitish blobs. This is arsenic, and they hope that they won't break, and they live with the very little phosphorus which they find. They have a rather difficult life, and so we haven't found life at 2.0 on Earth so far. I don't know where we'll find it, but I'm going to move on to something else now. Another one of the important discoveries that our friend QFW said we would make in the next 50 years. It's a direct interface between brain and machine, which means that I have a skull. I would like, really, wouldn't you like to take a USB flash disk, sterilize one, and implant it behind your ear? And you can put all the Encyclopedia Britannica very easily, zack. Then you know everything, go to school and you know everything fantastic. Or this was the input, but it could also be the output. For example, you think of a book, zack, there it is, put it in the printer, and it's done. Very useful. Don't laugh. We'll carry out an experiment with this. Well, before doing this, I phoned my friend Mozart, Wolfgang Amadeus. You might have heard of him. And big brain. Now, this is one of his scores. Please note one important thing. He didn't erase anything because Mozart was the sort that when he started to write something, it was all right. And Fermi never erased everything. What does it mean? It means that Mozart could hear all the music from the beginning, and then he already had the other symphony coming up, but then he had to take the pen, it was a quill, and light the candle and write it very, very quickly, but he was limited by the quill hand, the candle, no heating, and like. So I said, let's try and do something. And he agreed. There he is. I've put a system on sound system on Mozart, and so with the help of our sound engineers, we can see how Mozart thought of a symphony of his. I'm talking about Symphony number 40 in G minor. This is the famous, this white line which goes across all the components of the orchestra, the horns, the violins, the strings, the drums, is how Mozart thinks. Mozart must think of the whole orchestra at the same time. And he had it in his head like this. He could hear it. Imagine if he could put it directly in the USB instead of writing reams of paper on it. He would have written 4,000 instead of 41 symphonies. So we decided to carry out an experiment. And here I need a volunteer. I know it's not easy, but let's try. Because we're going to have something like this. This happened after I wrote my book. Time showed here the interface, which is something I'm going to do. I don't know. Piero, would you like to? Mario? Would you like to come? You're an important professor. Jump up. Like an athlete? No? You're going to use the steps? Okay. I would also like to talk about genetics, because Mr. QFW has said that in the field of genetics we'll be doing a lot of new things. I talk about it because modern genetics was started by a physicist, Schrödinger. It existed before, but in 1943, Henrik Schrödinger made a very important discovery, and there were conferences which ended up in a book that is available in Italian too, and which answers the question, what is life? It's a small little booklet. I think it's published by the publisher's house Adelphi, but very difficult, but it's very interesting because he started from a very easy observation, and he said, how do those Habsburgs manage to transmit that terrible chin down the generations? Look at them, they're horrible. Look at Charles V of Habsburg. Look at him. Oh, that chin, horrible. And all the others, all the other Habsburgs, like right up to the last one, all had this horrible chin. So he said, how do they manage it? How do the small Habsburgs, as soon as they're born, to know that they must develop that chin, the daddy's chin? It's not such a trivial question, and the question is that life is the transmission of information. Of course, he was right. If you think about it, only 10 years later, in 1953, Crick and Watson understood that information, the secret of information of life, was transmitted by the double helix. And that's where genetics took off and has the wonderful results that we're all well acquainted with. Well, this worked quite well in the field of genetics. We also understood that probably in genetics there's also the information of life and how long we live for, which is something, again, which we will have addressed in 50 years, but we're not clear about this yet. I want to talk about another experiment I'm not doing with a human being, live human being this time, but it's quite impressive. From a conceptual point of view, and that is to say, this one of the Methuselah flies. These are Drosophilas. And biologists have done all sorts of things with fruit flies or Drosophilas because they're very happy fruit flies. They live on fruit, and then at a certain point in their life, the females, here they are, depose eggs on fruit where they live. Now, this in California University did something, played a trick on them. That is to say, they took the eggs that had been laid by these females, and they blocked development, and they allowed them to develop when about half the eggs had died. So they left them to develop, and they allowed them to develop only when half had died, which means that only half of the eggs, and maybe they were the strongest and most, okay, fine. They went on. They went on with their lives as fruit flies, the females again, and then again half the eggs. They blocked them, I don't know, with temperature or something. They didn't let them open until half of those had died. And so you're back to half, so on for a certain number of generations. Luckily, generations are very quick with fruit flies. And after a few generations, I can't remember how many, but it doesn't matter, within a year, they produced fruit flies that were exactly the same as the started one, but that lived 4 times as long as the original ones, 4 times as long, without doing anything else. So they're simply selecting, blind selection of their genetic heritage. It reminds us of the Tarpeian rock a little bit, and the weaker children being thrown down it, but it's very simple, and it explains that the secret of longevity is also in our genetics. So you and I have to choose our parents, our grandparents, our great-grandparents, and our great-great-grandparents very carefully if we want to hope to live quite a long time, for example, 150 years. Yes. In that, for example, this will also be understood by the time Halley's comet comes back. Probably there'll be a child who will see it 3 times. And if you think about it, now the person who sees Halley's come back twice is quite rare, but 3 times, no. Yes, Didimo, who writes for the, his name was Rinaldo De Benedetti, saw it in 1910 when he was 6, and then he saw it again in 1986. But the second time, he saw it through the probes. So thank you for reminding me, but let us say it now, because Halley's comet is the mark of the technological development in 1910. For the first time was photographed, as I was saying at the beginning. So the first photograph, previously it had been drawn or painted, but that was the first time it had been photographed, the comet as it was. The next time we put probes and spacecraft in it, which is not a bad in terms of a technological development. Next time round, I wonder what we'll do to it. Probably we'll capture it. And Didimo is the father of scientific popularization. He invented it while he was being persecuted by racial laws. Are you telling me that I will be seeing it again? No, it's not your right yet. I don't think you will. But thank you very much for having recalled Didimo. Yes, it really fits what I was saying. You'll see that in 50 years there will be a child who will see it 3 times and live about 150 years, which is not that bad. But at that point, I think we have also to discuss how we're going to get there. And this is what QFW was saying. So we need spare parts. Spare parts are not so easy because what does it mean? What does spare part mean? Well, if I'm trying to run after a lizard, you might have done it. I take it and hold on to its tail. It'll give me its tail, so to speak. And you'll see that a week later, its tail's growing back. Here you can see the tail is growing back. Here you can see a lizard. You can't see it, but there's also another example, a crab here. And you can see that, in fact, and again, here you see this big crab, which has a lovely claw, chela, and the other one, it was lost probably in a fight or who knows, and it's growing back. It's a small claw or chela, but it's growing back. While if I take one of your arms and pull it away, it probably won't grow back. I'm very sorry for you. Why? Because you're more evolved than a crab. Not much, but basically, So I would like to try to reproduce this, that is to say, to have spare parts. And so here there's a big struggle between the method which starts from stem cells, which, as you know, you all know about it. I would like to say that at the beginning, I would like to remember, as Schrödinger was saying, who didn't know about it but had imagined it, there are the all-powerful ones, which are very few and must be able to differentiate and produce the 260 different types of human cells. I think they're between 250 and 300, which all start from that, and then progressively they differentiate, they become pluripotent, and then they become very specific. For example, if I cut myself, cells will reform and form a scar, but if I cut an arm, they're not able to start again and create a very complicated system, bones, nerves, muscles, and so on, to recreate an arm, because to do those, you have to go back and you have to start from the original cells. This is a major problem and has been so far, because the only way was to use, as you know, the stem cells, the embryo stem cells, which created a panic with the Roman Catholic Church, a big major problem. But luckily last year, in fact, a few months ago, they awarded the Nobel Prize, the 2012 Nobel Prize, who were to two people who are John Gurdon and Shinya Yamanaka. They worked separately, but they were able to go to the cell and enter the genetic contents of the cell and regenerate it, get it to go work its way back, so that it became a cell able to start, if it wishes to create a liver, heart, or whatever, eyelashes, anything that needs to be reproduced. So this is the future that is already here. And I think this is a wonderful Nobel Prize. And this, these iPS cells help us create spare parts. The alternative was a bionic human being, and the bionic human being is also developing, because also to have a bionic arm or a bionic leg, as we've seen, is not completely mad idea. It's still, currently, there's a competition between the stem cell system and the bionic cell system. And these are the latter being the so-called artificial one. But it's so well made that in the end it's connected with the right connections to the body, and it can work as if it were a normal limb, in spite of the fact that it is not flesh of your own flesh, as stem cells are. I don't know who's going to win in 50 years, but certainly we will be able to have spare parts good enough so that we can live, say, a long time and well. And lastly, if I would like to talk about a problem which is not trivial at all, because at this time we're all starting to think of a nice beefsteak. Everybody likes a steak, but unfortunately cattle occupy a lot of agricultural land, use up a lot of water, produce a lot of gases, in particular the greenhouse gases and methane. I suggest that meat should be produced in a lab, because it would free agricultural land, it would reduce the amount of energy required, and would also reduce by 80-95% the greenhouse gases, and would eliminate images that more delicate people are surprised by. That is to say, butchers would disappear. But for example, you could produce it. We're nearly there, because starting with stem cells, you could have a lot of meat in 2 months. With a system of multiplication of stem cells. There's a small fault that so far it cost about $100,000 a kilogram, which is quite expensive, even more expensive than the butcher around the corner here in Turin. So where do we stand now? Well, for the time being, we have those initial cells, and then this is where we are. We're not very far. No, it's not a great steak, is it? What we're really hoping to have is something like this. That is to say, NASA's already doing this with perch fillets, without the fish. I mean, it feeds the astronauts on it, but unfortunately they have no choice, and they're not so concerned about the menu when they're up there, so they just take what NASA gives them. But unfortunately, we're not yet able to go from one to the other. How do you move from one to the next? The answer is research. Research, as Mario was saying. The answer is research. And in Italy, it's not too successful. And I have dedicated my book, What's Left to Discover, is dedicated to people on short-term contracts. 11-syllable rhymed couplets. We in Italy have people who are on short-term contracts. They research for very little money, creating a future they don't have, getting less than what they give. Without short-term contracts, no discoveries. We want contracts. We want certain news. Quietly, with admiration, this is what a real baron of the university has to say to you.
Grazie, Professor Bignami.
Thank you very much, Professor Bignami.